Okay, picking up where we left off. The other option, if we are multiplying, would be that the number is on the inside of our function. In that case, we would call it a horizontal shrink or stretch. The mathematical notation for that would be a number inside of the parentheses right there on the x, again with multiplication. That we understand again that anything inside our function is going to impact our x column. But notice what happens when we do this is that we have to think opposite anytime it is inside. And so you will notice a change as we go from the function to our multiplication is that we use the reciprocal. To multiply our x column. This box right here on your cheat sheet is where people always have confusion, and it is mostly in the description process of it. So I try to make it as straightforward as I can. It's just kind of challenging, so bear with me here. The number that we see in the function itself, if that number is something bigger than 1, so the one that was in the function is bigger than 1, but it's inside, we still use the word horizontal. But you will always do this description by the number that you multiply your table by. So a horizontal, and then whatever we multiplied our table by just drives this next word. Well, if it was a big number in our function, we actually would end up multiplying our table by a fraction. So we would call this a horizontal shrink. By, and then the number you see here ends up being this number that we multiplied our table by. And again, this little number right here would be what you saw in your function. Okay, so if the number you see in your function is a fraction, so between 0 and 1, again, fraction. Inside, again, we pick the word horizontal. But because then when we multiply by it, we turn it upside down, a fraction turned upside down turns into a big number. And when we multiply by a big number, it will stretch by, again, the number that we multiply our table by. So by that reciprocal. And again, those numbers need to match. So this right here becomes way more important when you are describing your horizontal because it gets confusing when it is a shrink or a stretch. Match the word to the number. Big number stretch, small number shrink. But then also use the number you multiplied your table by. If you follow those two rules, you will always have the correct description. Okay? Number I multiplied by, match the word to that. Any questions for me on that? Okay, we now have vertical versus horizontal, shrink and stretch. So that's 4 different things. We're going to look at them very quickly because I'm going to use the same parent function every time to kind of speed up our process. But to see how this works, and to see, again, in the one that is a little more challenging to see the inside versus outside, we're going to use the parent function f of x equals x cubed. Now, I already listed that table out for you. This is the table of x cubed. If you went to your parent function, that's what you would see. 2 very important things is that you have the correct multiplication of the correct side of your table, but then also that your words correctly describe what our transformation is doing. So let's have our discussion here, first of all, when it is exponential. Now, this is the one I told you that people have trouble with, the inside versus outside. Is this 2 inside or outside of our function? Outside. It is outside. What would I have to see in my function to ever consider something inside of an exponential? Parentheses, right? And if you don't see parentheses, it can't be inside of that exponential function. Got it? No parentheses. That means this is outside. So first of all outside things impact our y column. So I will be multiplying my y column. All outside things impact my graph vertically. They impact my graph exactly as they look. So a big number, that is exactly what I use. Outside things stay the same. So I would multiply my outside, my y column by 2. So I would just go down this column. Oops, multiply everything by 2. I now look at the number I multiply by. It is 2. That is a big number, bigger than 1. So I would call it a stretch. Match again my description to what I multiply by. What I multiply by, again, if you can't tell, this is very important. The number I multiplied the table by. Match it to then my word. Okay? Now that I've done that, here are my ordered pairs to graph. Now, 16 runs way off my picture, but it can help me figure out the shape of this. So -2, -16, somewhere way down here, and I can't really graph that. -1, -2 would be here, 0, 0, 1, 2, 2, 16 is going to be way up there. But it would increase very quickly, squiggle through my origin, and increase very quickly. Just so you can see, if I were to compare that to the original would have looked like this. So the green is the original graph. Can you see how it took the green and it stretched it out vertically? Vertical stretch by 2. Okay, so I said we're going to look at these very, very similarly because isn't that almost look like the exact same function that we just had on the last page, right? This tiny little difference. What did I change? Parentheses, which now makes our 2 located where? Inside of our function. Anything inside will impact our graph horizontally, so I know it's going to be the word horizontal because it is inside. Anything inside my function will impact my x column, but this is where I have to remember that inside things are always opposite. So I will use the reciprocal when I do this, and you'll notice that I will multiply my x column by 1/2. Go down this column, multiply by 1/2 or divide by 2 is what multiplying by 1/2 is. Notice I am not changing the sign on anything. Okay. And then again, we use this number right here, the 1/2, to do my description. I'm going to put a 1/2 down here because it's whatever I multiply by. Well, if it's a 1/2, I use the word shrink because that is less than 1. The 1/2 here came from what I multiplied my table by, horizontal shrink by 1/2. And then I go graph those ordered pairs. Again, if I were to show you the original function in green, you can see from the original in green that I squished it horizontally, half as wide as it used to be. Questions? Okay, I told you we were doing 4 of these because now we are going to look at it with fractions. As always, the first question is it inside or outside? Is my half in this picture inside or outside? Inside. Inside impacts which column? X. And we use the word horizontal. Just like we saw in the last one, I will use the reciprocal. The reciprocal of 1/2 is 2. I will go down my x column because it was inside, multiply everything by 2. Use again this number right here, tells me what we just did, right? So it's a 2, that's a big number, so I would use the word stretch. Go graph those dots. This one is way even more obvious, the transformation that happened. Put a dot in the wrong spot here. -2, -1. If again I were to draw in the original, it would have looked like this. And you can see how I took that green graph and stretched it wider, twice as wide as it used to be. Horizontal stretch by 2. All right, the last one you're going to try on your own. You had your y column, which is correct, but anything y goes up and down, so that should be vertical. There you go. All right. Okay, again, this one moves to being outside. We no longer see parentheses in this. There can be nothing inside of this. Outside things use the word vertical, right? That's because it was outside is why I picked the word vertical right now. All outside things impact our y column exactly as they look. So I would use the number that is there, multiply my y column by 1/2, or divide everything by 2. I multiplied by 1/2, so I will use a 1/2 down here, and a 1/2 is a small number, so I would say shrink by the number I multiplied by, shrink by 1/2. Graph those dots. And one last time comparing to our original. Easier to see it like 2 and -2. But it took my graph and squished it vertically. Okay, we have now looked at how to graph reflections. Go change the signs on your x or y column depending on if it was inside or outside of our function. We've now learned how to do shrinks and stretches vertically and horizontally. But these were all on our parent functions. So what happens if it is a generic function? And I know this is not in your notes and it was supposed to be a check for understanding, but I want to show you guys you don't have to have a parent function to have a table of points, right? I really could create for myself a table of points from this picture, just list like the highlighted points in a table, and then you don't have to change your process at all, right? So I could just list -4, 0 in my table, -2, -2, 0, 0, 2, 2, 4, 0. And now I have a table, and yes, it's not one of my parent functions, but I can now just go do this transformation, which is outside of my function. Outside things, first of all, is called an ROX. Outside things always impact my y column. I would go down my y column and change the sign on everything, and now I have my list of points that I would graph to get my reflected picture. And then it becomes a connect the dots. So I would graph -4, 0, -2, 2, 0, 0, 2, -2, 4, 0, connect the dots, done. Questions on that? You will absolutely have questions like this on your DCA as well, where it is not one of our parent functions, but they're basically saying, can you look at generic function notation and understand what's supposed to be happening? So understand what those look like in generic function notation, not like a specific parent function. Questions on that? All right, we're going to skip this last one because that's pretty much what we just did. You guys are going to your My Math Lab homework number 14.